All right, everybody, we're back. We're going to do activity 3, although it says on the screen activity 2. And here it comes. Starboard. So we're almost to the point where we're doing a test level question, but not quite. Here is the one before test level, and let me just do a little heads up on the next one, which we won't do until our next one. And you'll see not much changes except you get a blank. Apparently we don't get a blank. There it is. Blanks, same kind of question, one extra part. That's the final test version type question here. So let's get this version started. Okay, and we have no spectators in the first one. If you don't cross spectators here, then you're going to try to connect things that have no business being connected. So get rid of that K minus. It was never there. Just pretend it was never there. That was a C minus. This K minus, same story. That was really a C minus. Don't cross it off and then forget to put the charge. I mean, there was something that spectator was doing, balancing charge. To ignore that is folly. Okay. So connect the conjugate partners. After you've crossed off spectators, connecting partners is simple. All you have to remember from your previous activity is that acid-base conjugate partners are different by only H plus. So in this pair, forget there was a question here. Look at the pair. Tell me which one has the extra H. Left, that's the acid. Which one has missing H? Right, that's the base. Let's go over here. Which of these two has the extra H? Right, that's the acid. Which one's missing the H? Left, that's the base. Huh? See? Okay. So it is not flipping between screens very well. This is the conjugate partner of which of these two species over there? Is it the one on the left or the one on the right? You'd have to say the one on the left. It has a difference of only H plus. So let's do that, shall we? Those are a pair. Okay. Which one has the extra proton? The one on the left. It's the acid. You put a pKa under that. Where can you find pKa's? I'm not going to tell you except one thing. The title on the page is pKa's you must know. You must find it. You must learn it. You will use it on every test in Orgo 1 and Orgo 2. These are just as important as the electronegativities you had to learn. Yes, must learn them. It's behavior you're learning, okay? It's the nature of these players in this game called organic chemistry acid-base version. And you're going to learn that an alcohol, which is the thing you put a pKa under there, has a pKa of 17 or 18. You pick one of those two numbers. Connect the other pair. Which one of those two has the extra proton? Answer, the one on the right. It's the acid. On that table that I told you you must learn, nitrogen shows up twice. If the nitrogen with the proton is a cation, like here, then the pKa is 10. You'll also notice this molecule's on the chart. So if you put pKa equals 40 under this, what are you doing? This isn't even the acid in this equilibrium. Yes, sometimes molecules under one condition are an acid, and under another set of conditions, not here, they're a base. So, guys, every time you do this, you better have one pKa on each side, because acids react with bases. Acid reacts with a base to create this acid's conjugate base, and the other acid's conjugate, the other base, its conjugate acid. There, pKa 10. Okay. Now you've got to learn, there's a question I didn't ask. Oh, wait, there is a question I asked. pKb. All right, if you're not acting like an acid, then you're a base. And you're not going to memorize pKbs. You're going to learn that for a conjugate pair, this is true mathematically, and it all comes from the Ka for an acid, equilibrium constant for an acid. You do not have to derive it. I did it in the book. I've done it on 3 or 4 videos. I'm never doing it again. All you need to know is this fact. pKa for the acid plus pKb for its conjugate base equals 14, end of story. I don't know why I didn't write 14. There you go. So if I know the pKa for an acid, the pKb of its conjugate base is 14 minus 17, because the acid's pKa was 17. And that's a strong base. With a negative number, the P is strong. So that's a strong base, and it came from a very weak acid. With a positive number, the P is weak. Whether we're talking pKa or pKb, the story is the same. Strong means it reacts readily and has a negative P. That's not this one. That's strong. Weak means it has a positive number and it doesn't like to react at all. Okay? So this one doesn't like to react at all. And we're going to find out its base doesn't like to react at all either. How do I know that? Because pKb is positive. How do I know that? 14 minus 10 is positive. That's a weak base. It's supposed to be a plus sign. I didn't need the plus sign. How about just 4? Okay. So the most reactive thing here is this strong base. It's the only negative here. So it should make sense that the equilibrium is going to push away from that, because strong means reactive. We don't like it. We want to get rid of it, make it more stable. But I'll tell you an easier way to pick the arrow that should be circled. And it's all based on pKa's, which you are going to put up here. That way, this is just an easy thought process. Look at the 2 pKa's. 10 on the right, 17 on the left. I didn't tell you yet, but P is a log scale. These are powers of 10. So a difference of 7 is really a difference of 10 to the power of 7. This is 10 to the power of 7 more acidic than this one. This acid is 10 to the power of 7 times more acidic than this one. We always react away from a more reactive acid and towards a less reactive acid. Circle the arrow that points to the bigger pKa. There. You get your point for your circle every time, as long as you wrote the right pKa's down. Okay, and pKeq is calculated from pKa. We'll do it in purple, and it's always the same calculation. You take the pKa of the acid on the left, 17, and subtract the pKa of the acid on the right. pKeq is negative. Oh yeah, that means reaction. 17 minus. That's not negative.
7, yeah, it's not negative.
Bad, dude. Bad. Come on. That was a blatant mistake. All right, it's positive, right? And positive means it doesn't like reacting that much the way it's written. It really prefers going backwards, which you already verified there, didn't you? Yeah. And once you've done pKeq, which is A minus B, A is the acid on the left. B is the acid on the right. Every time when I do it down here, it's going to be the same. Okay? And that's not hard math. And KEQ, say, I don't know how to do log stuff, Dr. Whitaker. That's okay. You don't have to. KEQ is 10 raised to the power of the negative sign of your previous answer. -7. That means you have, if you think about it, KEQ 10 to the -7, that's 1 over 10 million. 10 to the 7th is 10 million. 1 over 10 to the 7th is 10 to the -7. That means you made one of these molecules in the product side for every 10 million of these that you didn't react. Yes, this equilibrium favors the left side by a lot. We actually have a number now. So if you want to take the H off of an alcohol, using an amine is a terrible idea. Yeah, I would use a stronger base myself. So here's the story down here. Connect the pairs. And if we don't do this, then we won't realize that that is an alkyne. Alkynes are anything with C triple bonded to C. They are a pair, aren't they? Which one has the extra H? Well, it's the H I circled, everybody. You have to learn that an alkyne at the end of a chain like that has a pKa of 25. And the other pair is this pair here. And that's the H here on this one. That's an alkene. Not as acidic. If you want to know why, you can read the book about that. It's 10 to the power of 20 less acidic. pKa, sorry. 45. Wow. Yeah. It looks like I'm picking equilibrium that don't go forwards today. That's just bad luck. Oh, I made them the same color. Misleading. Well, this is a good test. If I want to calculate pKb here, what numbers do I need every time? Well, I need 14 minus the pKa of something. Let's see who's been paying attention. Is it the 45 or is it the 25?
25.
Did somebody say 25?
Yeah.
Yeah, because they have to be for the conjugate pair. Don't give me some random unrelated molecule for this. They must be connected so that you can use this number for the acid to calculate pKb for its conjugate base. 14 minus 25. We have a wicked strong base here. This one's even a more wicked strong base, I'm pretty sure. pKb 14 minus 45. Oh yeah. That's one of our strongest possible bases in this course. Yeah. Hey, what did I say about circling the arrow? Which arrow do I circle? The one that you go with pKa's and you point towards the higher number up here. 17 is higher than 10. 45 is higher than 25. So I'm expecting another positive pKeq and another negative 10 to the negative KEQ. pKeq is always the left acid minus the right acid, pKa. KEQ always 10 raised to the negative of the previous answer. So big time favoring reactants. And I think we're done with that exercise. I'll make it due at 12:30. Basically just got to copy what's on this screen here. Everything valid. I know it's a lot of work, but you've been busy. So I will stop our share. Take a screenshot now. Well, I can't now. Sorry.